Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter, we're going to talk about random forests as a data mining technique. So, what is a random forest, or otherwise known as a random decision tree? The answer is really very simple. Instead of creating one decision tree, we create many, hundreds, even thousands of trees that are going to do the classification or regression algorithm. And then at the end of it, we're going to take either the mode, so we'll basically poll and ask all the classes, all the different trees that you created, what did you guys decide was going to be the win or loss for our example? And it's going to take the most common answer. Think of this something along the lines of Star Trek and the Borg. There's no collective leader. They just weight all the decisions together. And that's how it's done. So the purpose to a random forest, and what makes them so useful, is that they correct the decision tree habits of overfitting to their training data set. Their overall accuracy is a little lower than gradient boosted trees, but it's still a really solid method of enhancing a decision tree. In other words, this is a simplified view. With a random forest, we create multiple trees. You see tree 1, 2, and 3. And then we have a voting process. Each tree says, I think the classification, the first tree says it should be A, the second says it should be B, and the third says it should be B. So majority voting comes out and we decide that the classification is going to be B. So each tree has an equal say into what they think the correct answer is. The random forest is actually a special kind of tree ensemble learner. They're very similar, but it's one of the decision trees. It supports both categorical learner and regression learner. So you see under random forest, there's a random forest learner and predictor and a random forest learner and predictor regression. As I mentioned, random forest is a special kind of tree ensemble learner. In fact, they share the same underlying code in KNIME. You can configure the tree ensemble node to function exactly as the random forest node. So the tree ensemble learner just offers additional configuration options that aren't available in the random forest node. So for right now, I'm teaching you random forest. You can look at the tree ensemble and have even more additional capabilities. All right, so let's look at a random forest. And a lot of this still looks the same. I've still got a learner and a predictor. And when I configure the learner, I've told it it's the opportunity result and I've left all columns in play. I'm using the information gain ratio, which means I'm using a C4.5. You can still pull in the Gini index if you want to go down the other path and use cart. So that's still available, but I can now tell it the number of models I want to generate. And each model will be different. That's what's going to be so great about this solution. And from here now, I've got two outputs. I've got the out-of-the-bag predictions. So this is what happened to the model, the source data that was coming in for training. And I've got the opportunity, the probability for it being a win and the probability for it being a loss, and the result that I've chosen, and then the level of confidence I have in that result, and the number of models that contributed to this solution. So that's also kind of helpful to look at and understand the voting that has occurred out of 100 models. Now, there's also within here an attribute statistics, the second output part. And I don't know why KNIME is showing this kind of funny, but it is. What it should be showing me here is the row ID, so each column in my table, and the number of times that column was used at split level 1 or split level 0 and then 1 and then 2. so that you can actually get a sense of the most important columns in here appear to be elapsed days in the sales stage change count, and the revenue from the client in the past 3 years. They're the most common fields that are used in determining the trees. And then the candidates 1, 2, and 3, 0, 1, and 2, actually specify how many times that occurred, how many times the attribute was present when the attribute was evaluated. So if you want to, just an optional note out of here is you can view the tree ensemble statistics. So I can see there was 100 trees, the depth, the maximum number of the maximum depth, the average depth, minimum number of nodes, maximum and average. And you can also view from here the tree statistics. This will tell me for each individual tree the number of levels that were in that tree. So there's 100 rows here. For each one, the number of levels and the number of nodes that were on that tree. That can be useful. I also find it sometimes helpful to be able to send this out to a PMML, predictive model markup language. What I'm doing here is I can extract the model and put it in a format, all 100 models in this case, and I can put it in a format that's accessible to other applications. So maybe, like I said, you want to run this model in Python or Java, any language or R. Anybody that supports PMML, you can export it basically out of KNIME. So they have a PMML writer and PMML reader, by the way. So you can read and write models that way. So in my random forest predictor, I still have the same thing. I've appended the confidence levels so I can use them in the scoring. And instead of the scorer node, I thought this time I'd show you the Java scorer node. It's just a little more interactive version of the scorer node. In interactive view, what you can see is you can generate this as a table because it's like all JavaScript views. I can see now all the same information, so the predicted versus the actual, so I can see my percentages. So basically there's my precision, and here's my recall across here, my true positives and my true negatives, all highlighted for me. And then at the detail level, recall and precision I can show out this way for the and sensitivity and specificity and the F measure. And then finally the overall accuracy and the overall error, which is just 100 minus the overall accuracy gives you the error. Cohen's kappa telling me this is moderately accurate, basically. I correctly classified 20,750 and I incorrectly classified 2,658. That's our version right now of a forest, and the next chapter we're going to take a look at gradient boosting. Alright, so I've updated our results comparison charts from the last chapter and now added the random forest results in. And what we can see is the random forest in this particular data set has actually produced some significantly better results. We've gone from a sensitivity on the, again, I'm trying to focus on the wins here. We've gone from sensitivity of 64% to 69, almost 70%. So that's a significant boost. We've also increased the sensitivity or specificity of the values as well. So the overall model accuracy is doing much better. And so on this particular data set, if I'm staying with trees right now, at least random forest appears to be my best solution. That completes this chapter of the class. Feel free to move on to the next chapter.